Everybody, welcome. Hope everybody is doing well. So today's plan is to go through contrapositive proof, which is the topic in chapter 5. So kind of learning our second proof technique beyond direct proof. And just so you know, coming up on Monday, we're going to look at a third proof technique called proof by contradiction. So I do think it's good plan to get some practice in with contrapositive over the weekend before it might get jumbled up with proof by contradiction. Before we get going, I just want to say, well, first of all, happy Chinese New Year to any of our Chinese students that are listening. And secondly, I graded and posted homework 2. So I just want to point that out to you. The solutions are up over here. I uploaded the attachment with my comments, and I also put some comments. Just if you look at I think the grade, if you click on your assignment, hopefully you can see my comments. So generally speaking, I would say the work is looking great. I'm really impressed. The proofs are looking really good so far. I think everybody got at least one of them nailed really well, and maybe some things can be cleaned up. So I would definitely encourage you to, even if you did well and there are some comments, to take heed of those as we move on during the semester. Kind of the expectation of your proofs is going to go up as we move through the semester. So things that I might be commenting now and letting slide a little bit, that might not be the case later on this semester. So I get that we're all kind of coming in and not quite sure what's expected for a proof. And I'm not going to start deducting for all sorts of little things just yet, but hopefully we're building towards there. And the goal is that you're going to be able to take upper division math classes that are going to ask you to prove things, and you've got a nice base to work on from that. I wouldn't want to throw you guys into a class that's going to ask you to prove a lot of things without kind of knowing what they're going to expect in those classes. The other thing I just want to mention is I know that students are working together on things, and that's great, and that's totally encouraged. That's a really important part of the process. It hasn't been an issue, but I just want to make sure that it's clear. And you guys are doing it just fine. That when you're working with someone on proofs, you guys should be developing your own style and your own proof. So it's totally fine to share ideas. It should be sharing. So if someone's explaining what they did on the proof, you should be asking them questions, making sure that it makes sense to you, and then going home and writing things up in your own way. So I shouldn't be getting proofs that are done exactly the same way, even if you've worked with other people in the class. So just be sure, if it's not clear what is allowed or not allowed in terms of collaborating with other people, just let me know. I'm happy to clarify that. So before we get started for today, are there any questions, any general questions? Okay, so then let's take a look at the worksheet 7 for today, which is proof by contradiction. Excuse me, proof by contrapositive. Contradiction is next class. So in the video that you guys watched before today's class, kind of went through kind of what is the contrapositive of a statement, and then how do we use that to develop a new proof technique called contrapositive proof. So the good thing is it's really just another direct proof, sort of, but the thing that we're going to prove directly is this instead of this. And the reason why this is just as good, this being this one over here, is because these two statements, P implies Q, not Q implies not P, are logically equivalent to each other. So depending on the truthfulness of P and Q, they're going to give us the same output in terms of the statement being true. When P implies Q is true, not Q implies not P would be true. And just the caution here is you don't want to confuse contrapositive with the converse, which is more simply switching the hypothesis and the conclusion. And so when you do that over here, you get something which has different truthfulness as the original statement. So this is a totally different, it's saying something not totally different, but it's saying something different. And so proving this is true doesn't guarantee that this is going to be true. Any questions about contrapositive statements, how to take a conditional statement and come up with its contrapositive?
The converse would be true if it was if and only if, correct?
If it is if and only if, that's right. Then it doesn't matter, right? Because you're basically trying to prove the first thing and the converse. That's right. You would need to prove both of those. Yeah, so with an if and only if, the ordering doesn't matter. With a more simple conditional statement, then it does, yeah. Okay, so how contrapositive goes, just some suggestions would be, I think, before you get started, definitely good idea to identify what is statement P, what is statement Q, and then before we get too far into the process, negate each of those statements, which is why we've been practicing negations. And then once I've got those negations, then we're gonna kind of do a direct proof for the contrapositive statement. So we're gonna suppose not Q is true, and then work our way down to showing that not P is true. And then, at the end of the proof, maybe as we're first doing this, it might be nice to just write a reminder that, okay, we proved not Q, not P. That is logically equivalent to P implies Q. Okay, so let's take a look at an example and maybe see like why we need another proof technique, like where maybe a situation where direct proof might fail us, contrapositive proof might give us an alternative way. So let's say we were trying to prove this statement down here. So we want to prove that if this expression x squared minus 6, x plus 5 is even, then x must be odd. Okay, where x is some integer. And so, if I wanted to do this by direct proof, then we would suppose that P is true and then try and show that Q is true. So if we were doing this directly, we suppose statement P is true, x squared minus 6x plus 5 is even. So just kind of picking up on how some of these other proofs have gone directly, then we can go from this statement to then saying, okay, if that's even, it should equal to A for some integer A. And then what we typically do is then try and show that x is equal to 2b plus 1, right? Because we want to show statement B was that x has to be odd. So we kind of start at this point over here. And we're trying to get to this point over here. And so the question is, like, what would the next step be once I get this? You could do something, I suppose. You could try and do the quadratic formula or some other things. But the point being, maybe it's not that simple. We need to do some more advanced stuff. And so if we kind of flip this into a contrapositive statement, let's kind of see how that might help us in this case. But any questions on kind of this kind of outline that we have if we wanted to try and do this directly? Okay, so then if I'm gonna do this by contrapositive, then kind of the first step would be, let's identify not Q and not P. So if the statement Q is that x is odd, we negate that by saying x is even. And this is why it's really helpful to try and negate things sometimes without using the word not. First of all, I feel like it's kind of insulting to define something by what it's not. Like we wouldn't say there's men and there's not men. I don't know. People would like to be identified as something other than not being in this group. So secondly, it would be really helpful to know what does it mean to not be odd. Okay, it should be even. So statement Q negating gives us this. P not P gives us x squared minus 6x plus 5 is odd. And now we're going to try and prove that this not Q implies that, not P. So first statement, when we're doing this by contrapositive, here's kind of how the proof might look. So we start by assuming not Q. Suppose that x is even. And this has a little bit similar feel to a bunch of the proofs that we've been doing so far. So now this is like, okay, we start with something really basic being even, just x, and then we're going to try and work our way to showing that the more complicated thing is odd in this case. So we start with this being not Q. And again, if you're kind of thinking about what would the outline look like, we're going to start with that, and then we're always going to end with showing that that is odd. Excuse me, that would be not P. And then the question is, okay, how do we connect those two highlighted statements? And again, I hope these kind of, although they're different because we're working with different expressions, that these, if this is even, this thing is odd sort of proofs are, you're getting some, at least tricks that seem to be working with some of these problems. So in this case, we kind of say, okay, what does it mean that x is even? That means it looks like this. And then again, these should feel pretty similar to what you did on some previous homework. So then we can plug this in for x, which is easier to do rather than solve for x, which is what we would have to do if we did this directly. So now I can substitute x, even x into this expression, simplify, and then kind of do the typical trick where we then would like to show why is this thing, sorry, we wanted to show that it is odd. Yeah. So why is that thing equal to 2, say, b plus 1? And then it becomes algebra, right? We need to somehow get a plus 1 in here. So I can do that by breaking up the plus 5 into a plus 4 and a plus 1. And then pulling out the 2. So then this becomes the 2. This stuff over here is the b, and now we've got it as 2b plus 1. So that's kind of the gist of contrapositive proof, and maybe why it's nice addition to our kind of proof arsenal beyond just doing things directly. Any questions?
When you're negating Q, how come you don't have to include 0 as well? Like, why wouldn't you say suppose x is non-negative?
So x is
0.
X is an integer. 0 is an integer, and 0 is an even integer.
Oh, okay. Okay.
So yeah, as far as integers go, there's only 2 categories: odd or even. Yeah, and that's kind of a good thing to just mention. That might not be clear that if you have 0. It can be written as 2 times 0, so that makes it even because 0 is an integer.
Okay, all right.
Other questions? I will just say, when you can do things directly, that's the preferred proof technique. That's kind of the easiest logic to follow. So I think as you're proving things, you might want to start out thinking, is direct proof going to work? And if you run into a roadblock on that, give contrapositive proof a shot. I would say that might not be your first reaction to proving things. And when we do prove things using a technique other than direct proof, then in these proof writing guidelines, it says to indicate your proof technique, not like I did here, but indicate your proof technique right away so that the reader understands. Like, it would be weird if I'm trying to prove this statement and then the first thing I see is this, because there's nothing in this statement about X being even. And if you tell the reader, okay, this is contrapositive, then they'll make sense. It'll make sense why you started your proof with that line. Okay, so we've got a bunch of proofs to practice today. Any requests? Any of these look particularly interesting to you? That we can do some together, and then I'd like to have some time for you guys to practice them as well.
Could we do 3?
Yeah, we can do 3. I would say let's not start with 4. I don't think the first one we should do has power sets in it, but we'll work our way towards that. Sure, we can take a look at 3. So 3, yeah, let me just copy this and find some space to work this one out. Okay, and so maybe just thinking about if we were to do this with direct proof, right? So we would start with P, statement P, I guess I should say this is P, and we would work our way to Q. And kind of what's a little bit awkward about this one is, again, we're kind of like starting with some negative statement here that says, well, what does it mean for a squared to not divide b squared? Well, then that would mean like b squared can't be written as a squared times some integer, right? Because by definition, what it means for, just to say like integer p divides q, this means that, right, q can be written as p times some integer. So if I'm trying to do this with direct proof, it's not clear to me maybe where I would go next with this. So let's see what it looks like when we try and do this with contrapositive proof. So let's identify what not Q and not P are. And if A doesn't divide B, then the negation of that would be that A does divide B. And the negation of P is that A squared does divide B squared. Right? And then we start with Q, not Q. And here I'm just kind of adding a line at the end, which might be justifying, that we did this, that contrapositive proof is working out, and in the end, this is equivalent to proving the original statement. So maybe I'll say, I'll just say that that little piece that I put at the end is maybe like an optional thing. It's nice to just conclude that for the reader. But since we kind of indicated our proof technique from the get-go, I don't think that it's necessary to do that. So this is the general plan. Any questions about why we're starting like this and why we're kind of working towards that final goal? Does anybody have a suggestion about what we can do then after this assumption that A divides B?
B is equal to A times some integer K.
Yep. Yep, and it's nice again, every time we introduce a letter like A or B, to just let people know what that is. Is that a set? Is that a function? No, these are integers. And now we have another letter that we just introduced, and we let people know that is an integer too. Yep, makes sense. We are just gonna write out what this means by definition. Okay, and if we're trying to think about where we need to go next, keep in mind that if I want to show that A squared divides B squared, just to put some scratch work down here, right, we would like to show that B squared is equal to A squared times some integer M, different maybe than the first one. And if I can prove this, then that by definition would tell us A squared divides B squared. So any thoughts about what we could do next to try and take this expression over here and start to move towards this expression over here?
You just square both sides and then K squared could equal M.
So yeah, if B is equal to A times K, then we can square both sides of that equation. That's right. And maybe the reason why that's a good observation is that would give us a B squared on one side and an A squared on the other side. So squaring both sides gives us that B squared is equal to A squared times K squared. And, you know, that basically is where we needed to get to, right? Okay, where now this integer that we wanted to find is actually the original K that we had squared. And that should wrap it up. I'll get rid of this. That was some scratch work. That's a contrapositive proof for that statement. So it's really just like one extra step, right? Which is let's negate each of these things and then do a direct proof of the negations flipped around. Any thoughts or questions about that process? Okay, well then you're ready to do these on your own. So let's start with question 1. That's usually a good place to start. And the idea here is we want to practice contrapositive proof. So even if you can do these directly, which you probably could do one directly, let's practice using contrapositive proof. So let's start with 1. And that's the goal for your groups. And if your group happens to finish up 1, then move on to 2. And then we'll handle that one together. We'll talk about the power set one together. But any other questions before we set up the breakout rooms? All right, so the rooms are open. And Lindsay and I will be circling through to give you guys a hand. Again, it's really helpful if you get those shared screens going. That's great. So how far did you guys get, Diane, Christina, Mitchell? You guys get through the first one?
We got through the first
And
one.
the
We're
second one.
halfway through the second one.
Okay,
Mhm.
cool. So yes, I think that it seems like this one went okay with the groups I was talking with. So this would be kind of the gist of it. And again, if you're having some trouble, like what should my starting point be on these, especially when you're told like prove this by contrapositive, then whether you want to write this out or not, I think it's good to write it out. It might be useful to just make a note of what the negations of these are. And then you've got your kind of blueprint over here, and you just plug in not Q, not P, and then try and connect them.
Mhm.
And so this is a pretty similar trick that oh, I realized that I'm not sharing anything, sorry. Sorry. That seems to happen at least once a class. That was the one time, I hope. Yeah, so when you're trying to do these, yeah, it might be useful to kind of first just write the negations, and then you've got this general proof outline, and just kind of plug in where you're starting, where you're going, before you start to get too far into the proof. Were there any questions about that one?
No, once we did it backwards, it made seeing it forwards a lot easier.
Say that again, sorry, Mitchell.
Sorry, I thought we were talking about number 2, disregard.
We will. Okay, yeah, so let's take a look at 2, and kind of the difference here is that this is a if and only if, right? So this means we're gonna have to prove 2 things. We're gonna have to prove, well, in general, P implies Q, and then we also need to show the converse, in this case, that Q implies P. And so we're gonna prove each of these things using contrapositive. So if I'm gonna prove this by contrapositive, maybe I shouldn't use this notation, then what we would want to do is say not Q implies not P. And if we want to prove the reverse direction also by contrapositive, then we use the same sort of trick. We negate each of them and then flip the hypothesis and conclusion.
So the converse of a contrapositive is just the negation, kind of, right?
The converse of contrapositive, so when you take the converse of anything, it switches hypothesis and conclusion. Yeah.
Mhm.
So I think maybe the way to think about this is when you're doing a biconditional statement, yeah, you need to prove the conditional statement, you need to prove the converse of that conditional statement. And so if we're going to do each of those by contrapositive, I think it might be useful just to think of these as like 2 separate proofs, right? So we need to prove the forward direction by contrapositive, and then we'll try the reverse direction with contrapositive. So when I'm referring to forward and reverse, this is what I mean. So let's maybe this might be a good way to think about this. When we're doing biconditionals, it's useful to kind of indicate which direction you're doing. So in this case, we'll start with the forward direction. That's usually how it goes. And we'll indicate how we're going to prove the forward direction. So this is like a little editorial note here, which is going to help the reader follow your logic. And so if I see this before I read the proof, I just make a note to myself. If you're curious, like how I grade these, I would make a note to myself and say, okay, did they start correctly? Whoops. Over here, and do they have the right last line? And you get credit if you know, like, I should start here and I should end here. Even if you mess up in the middle, you'll get a bit of credit there. So does someone want to share, if your group got through it, how you went about this?
We all agreed that we would start by supposing that x squared is odd.
That's right. So we're going to start with the converse, or excuse me, the negation of that. That looks like one word. Okay.
And then we subbed in 2a plus 1 for x and solved.
Then you plugged in 2a plus 1 for, so if x squared is odd, then kind of what's the next thing that we could say after that assumption? So what is this what you said? I'm trying to.
Yeah, that's basically what I said, but then I realized that I got the steps wrong. That we said that x squared is equal.
Yeah, that's right. That's right. So yeah, so when we're saying these things, like, yeah, usually you want like the next sentence to follow like right directly from the previous one. So yeah, if x squared is odd, that tells us x squared is 2a plus 1. For a integer. Great. Then what can we do here?
Yeah, you want to show that x is odd, but the problem that we had is we didn't know exactly how to get there. So we actually did the reverse first.
Okay.
And then that kind of told us what that had to be.
Okay. I agree that it seems kind of weird once we hit this point. Like, I want to say something about x, namely that x is odd. If I'm working towards x, seems like that I would take a square root or do something like that. And then I don't know if I have integers left over, right? That's the problem when you take square roots. So we'll come to the reverse direction, which I do think is going to be easier by contrapositive. I realize now that maybe doing this one by contrapositive, we kind of hit a roadblock here. So let's try doing one direction. You're totally allowed to do this. Using direct proof, we'll do one direction. Since it seems like the reverse direction did work with contrapositive, we'll hold out on the contrapositive part for that. I'll just say, when you're doing proofs on an exam or on homework, if you're not told what proof method to use, you're welcome to choose your own method. Some of the questions are going to say, prove this using this method, and then I've made that choice for you. So I'm going to scratch this. We hit a roadblock there. So we're going to prove the forward direction by direct proof. And if we do that, then what would our first line be here?
Suppose x is even.
Yeah. which are typically like really nice places to go because then we know what x is, and then I can say something about some expression that depends on x. I can substitute this in for x. So if x is even, then we know that it is equal to 2a for some integer a. And then what makes sense next?
You want to square it because you're trying to show that x squared is even. That's your endpoint.
Yep. So then that's right. We would like to say something about x squared that it's even. So now we can plug this in. And now we've got it written in the form of 2 times an integer. So that's one way we could think about doing that forward direction, doing it directly. And I think if you compare it to like the stuff that I erased, this seems like a more natural, intuitive way to think about that direction. Any questions? And now we'll do the reverse direction by contrapositive. So now we're on this piece over here, right? That's the reverse direction. Q implies P. If we do it by contrapositive, then what should our first line be for the reverse direction?
The X is odd.
Yeah,
Yeah,
x is
so
odd.
we start with not P, which is X is not even, which is X is odd. And I think like one thing that we might pick up on a lot of these even odd proofs is that it's easier to start with knowing what X is and then trying to prove that some expression of X is even or odd rather than go in the reverse direction. I think a lot of this proof is probably going to follow pretty similar to what we just did above. So then we know that x is equal to 2a for some integer a. And that what seems like a good plan next.
Square both sides.
Yep, square both sides. And then we do some algebra. So now we've got x squared written as 2 times an integer plus 1. That gives us what we wanted to show, which was not q, which is x squared is odd. Okay, questions about that one? Okay, if not, that brings us to power set proof. And so I would say these tend to be tricky for students just because power sets are trickier to think about than even and odd numbers. And so just recall that a power set of set A would be the set containing all of the subsets of A. So we've got power sets here. We're going to try and work with some negations. And again, this might be a good indication that proof by contrapositive might work because it's a lot easier to think about this being a subset as opposed to it not being a subset. There's lots of ways you could not be a subset, but the definition of a subset is a little bit more concrete. So our statement P here is the power set of A is not contained, is not a subset of the power set B. In our statement Q is A is not a subset of B. And so we're going to try and prove that not Q implies not P, which is if A is a subset of B, then we're trying to show that the power set of A is a subset of the power set of B. And actually, these two statements are logically equivalent to each other. So proving one is equivalent to proving the other. So here's where we should be thinking about starting and eventually getting to that point. And if you're working on your homework and you get totally stuck, at least this is a place to start, and you will get credit for kind of indicating that much. Okay, but now we don't have odd and even things. So it's same proof style, but we're working with different objects here. Now we're working with sets and we're working with inclusions. And so I will just say, kind of my observation from last class is we're all more familiar dealing with even and odd numbers. We've encountered them before. The definitions are kind of match our intuition. The set proofs take a little bit more time to get used to them. So definitely just kind of respect that and give yourself some time to work on those. So if we start with this assumption that A is a subset of B, anybody have a suggestion about where we could go next?
Wouldn't you have to show that if an element is in A, it's also in B?
We don't need to show that, right? I mean, you're right. That's what it means to be a subset. And since we've assumed that, we now can state that that has to be true. That's right. So rather, usually what we say is we state some assumption, this number is odd. And then the very next thing we do is we write out what does the definition of odd mean. So we've got A is a subset of B. Let's just write out what by definition that would tell us. That's exactly right. So this would tell us then if X is an element of A, we know that X has to also be in set B. And to kind of think ahead, if you're stuck at a point like that, we can similarly think about like, whoops, sorry, what would we need to prove in order to get to this claim? And again, we can kind of just work backwards from the definition of subset. Is that if something is in the first set, then it has to be in the second set. And again, the thing that you want to remind yourself is that the elements in these things are sets, right? They should be subsets of A. Okay, any questions? These are tricky, so please, if you're thinking I've got a question about subsets or power sets, I bet somebody else is having a similar question.
I have a question. So, do we always have to like bring in like X or Y or something, or can you just like prove something without bringing it in, just saying like, suppose A is a subset of B, then by definition, all of the elements of A are in the set B?
You could say something as well, and that might be fine in some cases. In other cases, you might find that it's actually nice to have to use symbols that are representing those things. So I don't want to say like a blanket statement that that's always going to be fine or you should always do it this way. I think that's reasonable if that kind of gets you stuck and you're like, I really just wish I had a symbol that I could refer to, then this might be okay. Yeah, but I think that could work, certainly.
Okay, thank you.
Yep. Okay, so we would like to show that any element in the power set of A has to be in the power set of B. And so what does this mean over here? This means that it's a subset of A. So let's consider some subset of A. So let's let X be a subset of A, and therefore it is an element of the power set of A. And again, what we're hoping to show is that X has to be over here. And I'm just trying to make my capital X's seem drastically different than my lowercase x's. So, right, before I could claim something like this, we would have to show that it is a subset of B, and that's why it would be in the power set. So I'm really at the point where I really want to show any subset of A is going to be a subset of B. And this little fact over here should be the statement that I need to prove that.
Can you say if
Yeah, go ahead.
if like the little x is in the set X, then we know it's both in set A and set B.
Yeah, so maybe let's say, and And since I used X over here more generally, I actually don't even necessarily need to have stated this here, but yeah, you got the right idea. I'm just going to choose a different letter. So let's let Y be some element of this set X. That's right. And then what did you say next? Was that Nicole?
Yeah, so if Y is an element of X, then we know Y is in the set A.
Yep. Sorry, I ran out of space. So since every element of X is an element of not Y, of B, then we see that this set X has to be a subset of B. And that means it's in the power set of B. And I think we've connected to where we wanted to go at that point. But let me just kind of zoom out. And I think this is a case where we probably can clean this up a little bit. I think logically this is a good proof. Maybe the style some things may be stated a little bit redundantly. I think the suggestion about do we even need to refer to symbols here? Could we just say every element of this is an element of that? I think that probably could work here as well. I might just suggest that you kind of take a look at this and then think about how you can clean it up. So like if you're kind of working with others on these proofs, that process might look like something that we did together. And now you and the people you're working with see something like this. You know, it would be good if you all kind of go independently and try and just clean it up and write it up in your own terms. And that's great. Any questions about it? Okay, that was a lot of proof so far today. Yeah, so I will, I'll leave these as some additional practice for you and write up some solutions to them, but I think it's good practice for you guys to try these on your own and then look at the solution. And if you do have any questions, just let me know. Don't forget that you've got homework 3. I will just say that my plan for having these due on Thursday was that I was going to spend Friday grading them. That's not happened. So I do like using the weekend. So I'll push it back a day so that homework 3 is due on Friday. I will post homework 4. It's not going to be due the Monday, this coming Monday. Then we'll start to have homeworks that'll be due on Mondays after that for the rest of the semester, with maybe some exceptions when we have our exam. So one more day for this one. And while you're working on that, I'll get homework assignment 4 up, and then that one won't. So in other words, you won't have any homework to submit next week, actually. So this one would be due on Friday, and then the following Monday. Does that make sense? Cool. Okay, so if you do have some questions on them, I've got office hours, and you're welcome to give that a shot. One thing I'll say is there is a discussion board in Canvas. I'll kind of leave it for you guys, if you feel like it's useful or not, there's a little tab over here that says discussions. There's nothing here. You're welcome to just add a discussion and say, hey, I got stuck on this proof or whatever. So you're welcome to do this. I don't know if you'll find it useful or not. You're not required to do this stuff. It's not going to be graded. It's just a tool for you guys to find a way to collaborate. But it seems like you've kind of got some collaboration already going on. But if anybody is looking for some extra help or says or wants to find some other people to work with, just shoot me an email and I can try and help. I think that there are some that's already going on to some extent as far as I know. So that's great. Okay, well, we went 2 minutes over on Monday, so we're even. It's 12:13. Enjoy your 2 minutes. If you do have questions, I'll stick around. Otherwise, have a nice weekend if I don't see you before Monday.